Welcome to the video on nonlinear inversion. So in the previous video we went over the theory of linear inversion and a good example of coding from scratch. So check those out if you want to learn about linear inversion. So today we're going to be learning about nonlinear inversion. So this is when you can't easily separate out those model variables from the maths or the physics of the problem you're trying to solve. A good example of this is fitting Gaussian functions. So the first part, what we're going to do is we're going to go over a bit of the theory behind it, a brief whistle-stop tour of that, and then what we're going to actually do is try and fit Gaussians. But what we're going to do is we're going to try and fit it to infrared spectroscopy data from the output of massive young stellar objects. So when stars are forming, they have an accretion disk around them, and then they have expulsions from their poles. So we're going to check on and see, what kind of red or blue shift we can see, if any, from these emissions. But first we need to go over some theory. So the rest of this video is going to be about the theory of nonlinear inversion, and then the next part of this video, that will be about the coding with that interesting dataset.
So we're going to start from the same equation that we had in the last video, link in the description below. So we've got y here, which is the observed variable. We've got g, which is our data kernel that contains the maths or the physics of the problem we're trying to solve if it's linearly separable from the model, and m is our model parameters. But what if we can't separate g and m here? What if we can't separate that physical modeling into a matrix vector product? What if we just have a function? So instead of having gm, we have a function here, g of m. So this can be any kind of forward modeling, and this is a much more typical scenario that we have where we don't really know how to separate them. So then how do we go about solving this equation? So we still need to solve for m. So what do? We don't know m. So what we're going to do is we're going to start with some initial guess, some m0, something like, I think it could be this, or this is a good estimate. And then we're going to say, right, well, we want to get to m, so we need to add something to m0, a delta m. And now what we're going to do is we're going to try and refactor this to solve for delta m. So we've got some initial guess, and we're going to add some change in model parameters that we're going to try and estimate to that. So how do we then go from this equation now, which is g of m0 plus delta m, to something where we can actually solve for delta m? So how are we going to do this? Well, the first trick we're going to employ here is we're going to do a Taylor expansion of that g of m0 plus delta m. So I'm not going to go over what a Taylor expansion is here. You can find that in various places on the internet. But I'm just going to show you the first three terms of this Taylor expansion. We're going to assume that higher order terms are negligible for our purposes. So what we have is a zero order term, which is basically what this function is, our function that we're trying to solve at our initial guess m0, and then the derivative of that with respect to the model parameter is evaluated at that initial guess multiplied by the change that we want, and then there is a higher order quadratic term which involves the second derivative of that function g. So while some optimization schemes take into account this second order derivative, and we'll go over them in future videos, for the scheme we're going to outline here and the method we're going to use, we're going to assume that these are negligible. The second order derivative here is small enough that it can be considered negligible compared to the first order derivative and the function at m0. So we're going to just remove this part as well. So now we've got a form for g of m0 plus delta m in terms of variables that we can either evaluate or that we actually want to estimate. So for instance, the delta m here we want to estimate. The function can be evaluated at m0, our initial guess, and assuming that the first derivative exists, then we've got the first derivative of this function again evaluated at m0. So these are all things that we can evaluate. So this is going to be what we're going to try and solve, and as you may be able to see, it's essentially a linear equation that we need to solve for delta m. So we can use the exact same cost function we used in the previous lessons as well. The only difference here is that we're estimating an update to the model rather than the model itself. So we're doing that by linearizing the function in the area of m0 and plus or minus delta m. The problem here is that if our delta m update is too large, then our linear assumption fails. Some solutions to this are to just artificially limit the model update, so to make it much smaller with a coefficient, or to weight the model update towards 0 like we saw in Tikhonov regularization in the previous theory video. Okay, so that was a little aside, but getting back to our equation we need to solve and the cost function, a little simplification I've done here is I've replaced the gradient that we saw, the dg by dm evaluated at m0, with just the capital letter J here. So I'm going to call it the Jacobian from now on, as a term that you'll typically hear. So it's basically, whenever you hear that, just think the gradient of whatever function you have with respect to the model parameters. So this g of m0 term is essentially what you believe the observable should have been given your initial guess. So they're not going to be correct unless you're very lucky and you've got the model bang on in your initial guess. So when we take away the actual observables y, what you're going to be left with is a residual r. So I'm going to replace that later on with just the single letter r, and if we could see that now, you'd be able to see that this is the exact same equation we had before, but just with some different letters in. So we know exactly how to solve this equation, this cost function. We just do the derivative with respect to the delta m here, and then set that equal to 0. And if you check back in the previous video for the linear version of this, then the derivation is going to be the exact same, so we'll just follow that. So we're just giving the derivative here, and it shouldn't be any surprise to you given the previous video. So what's next won't be a surprise either. We're just going to multiply out the brackets, get rid of the 2, and then rearrange slightly. So as you can see, we've also followed the last step of rearranging for delta m, which just involves multiplying on the left both sides of the equation by the inverse of the Jacobian transpose times the Jacobian. So you can see how similar in form this is to the equation we had in the previous video for estimating the model parameter when we can have a linearly separable data kernel and model. Now you can do the same thing here that we did with the other equation in terms of adding any kind of regularization you want, but just be aware that that regularization will apply to the model update, not necessarily the model itself. So now the only thing to do is to add this delta m to our initial guess to get an updated version of our model. Now this is not necessarily going to be our final and global optimum model. It's just going to be an update that we provide given the linearization that we've had on that function g. So what we'll need to do is then re-update the m0, the initial model parameters, to be the new ones, and then go through this whole cycle again. So this is an iterative routine where we hope to update the model parameters that we're estimating from an initial guess to hopefully a global solution. So you might be asking, well, how do I know when it's a global solution? How do I know when it's the best fitting model I can find? Well, that's a difficult question, and especially the global one, as there may be multiple local minima that your model might fall into. But the easiest way to check on these and to check that your model is going in the right direction is to check the value of the residuals, check the cost function that you're using, and any other metric that you wish to observe, and to see if those losses are decreasing and those residuals are decreasing.
So hopefully that was interesting and informative. And stick around for the second part, where we're going to try and fit, with this method, Gaussian functions to the output of massive young stellar objects. So in next week's lesson, we're going to cover covariance of the model and the data. So we all know that measurements are flawed, they're never perfect and accurate. There is some error associated with them. And even some data or model points may be correlated. So we're going to see how we can actually implement that in our models next week. So stay tuned for that too. And again, if you like this video, please click like and subscribe, and hit the little bell icon for notifications when we get a new video uploaded. Thanks.